We have different ways of representing atoms, molecules. Molecules is what I mean, not atoms. So this would be, it's sort of a Lewis structure. Technically, a Lewis structure should show all of the lone pairs. And we usually only do that in organic chemistry if we're interested in those lone pairs. And so a structural formula is really a better name for this sort of a formula. Structural formula is going to show you how all the atoms are combined, and it's going to show them all written out. Structural formulas can be very tedious to write over and over and over and over again. So we only write them when we really need to. Then we have a condensed formula. And the condensed formula is generally centered around the carbons. If we look at this, we see that there are 4 carbons in a chain. They're making a chain, and then there's things attached to the carbons. And you can kind of think of the carbon chain as being like a charm bracelet, and the atoms that are attached to the carbons as being the little charms that are attached to each link of the charm bracelet. And so the condensed formula is going to show the first carbon and how many hydrogens are on that first carbon. 3. So we're going to go CH3, and then we'll write the next carbon. How many hydrogens does the second carbon have? So CH2. And then the third carbon, what's on the third carbon? 1 hydrogen and a bromine. So CH Br. And then, I'm running out of room, the fourth carbon has how many hydrogens? I don't know why I started to write 4. It's 3, thank you. So the carbon and what's attached to it. The carbon and what's attached to it. The carbon and what's attached to it. Here it's 2 different things, hydrogen and bromine, but they are on the carbon that comes before. So let's do this other one here. The first carbon has what attached to it? Has 2 hydrogens, CH2, and this guy down here, OH. And carbon 2 has what attached to it? 2 hydrogens. And then the next carbon has what? Just 1 oxygen. And then the last carbon has 3 hydrogens. So that's a condensed formula, or a condensed structural formula. It still gives us information about how the atoms are connected, but we don't have to write everything out. And you can do this on a computer. It's a little tedious with the subscripts, but not too bad. Drawing this out on the computer, it's really a pain. Sometimes we go a little further and we'll actually show this oxygen. So there's some slight variations. You might see CH2, OH, CH2, and sometimes they'll pop that guy up like that. So there's some minor variations. Oh, I made a mistake. I changed. You can't do that. There we go. Any questions? We also have line structures. Line structures take more getting used to look at, but they're really fast to draw, and so we use them a lot. So this is the structural formula. And in a line formula, we don't show the hydrogens. We just assume that they're there, where they're supposed to be. And so we take the carbons, and we're going to make a zigzag out of them. Because what's the geometry at each of these carbons? It's tetrahedral. So it's convenient to draw this out all straight and nice, but these are not 90-degree angles. This is a zigzag kind of deal. So here we're showing how the carbons are zigzagging, and then we don't actually draw the carbons. We just understand that at the end of each line is a carbon atom, with however many hydrogen atoms it needs to satisfy its valence. So if it's on the end, it's going to have 3. If it's in the middle, it's going to have 2. I can't remember what's next. Oh, let's do this one. So draw the line structure for this molecule. How many carbons do we have here in this chain? 1, 2, 3, 4, 5, 6. So the first thing we'll do is we'll use zigzag lines to make the 6 carbons. So I always, when I put my pen down, that's the first one. 1, 2, yeah, but it doesn't like that when I do it on the iPad. 1, 2, 3, 4, 5, 6. So here's 1 carbon, 2 carbons, 3, 4, 5, 6. The end of each line is a carbon atom. We don't have to draw the hydrogens. But here we've got something that's not a hydrogen on this last carbon. So then we're going to do a double bond and an oxygen. This point here, this corner, is the end of that line. There's a carbon there, and that carbon is double bonded to the oxygen. Let's do a different example. Let's go the other way.
So that's the end of it? That's like the end of the drawing?
That's all of it, yeah.
If I looked at that right there, I didn't know.
Right. It takes a little bit. So let's do some the other way. Oh, I don't want to do a really long one. Do a simple one first. It looks kind of like a sideways stretched out Z or something. Well, how many carbon atoms? 1, 2, 3, 4. So if we're going to draw the structural formula, we're going to have 4 carbon atoms attached in a line. And there's nothing else indicated on there. We understand that there are hydrogens on each of these carbons to satisfy the valence. Carbon wants 4 bonds, which makes this flat 90-degree thing really nice because you've got up and down and side to side. There we've given each carbon 4 bonds, and we're going to fill those in with hydrogens. So right now I'm just kind of introducing you to this idea, and then we'll be using these structures as we go along and talk about the different compounds. And if you're not understanding, you need to ask me and I'll clarify, okay? So what if we have something a little more complicated? What if we had something like that? Well, here we've got 1, 2, 3, 4 carbons that are in a line, right? A zigzag line. 1, 2, 3, 4 carbons. And sometimes it helps to number them. We'll do a lot of counting in organic chemistry. 1, 2, 3, 4. We don't do much other math, but we count a lot. This carbon number 2, what does this line mean? What's at the end of that line? Another carbon. So I'm going to draw a line here and put a carbon up there. Carbon 3 is attached to an OH. So I'm going to put a line down and put an OH down there. Anything that's not hydrogen or carbon is going to be shown. The carbons are shown as at the end of each line. But this line ends not in nothing, but it ends in an OH. So there's not a carbon here. This is the OH at the end. If it was a carbon, it would be like this one and we wouldn't write anything. Everybody with me still?
Do we do this only for carbon-hydrogen atoms?
We do this for organic compounds which will always contain carbon. And then if there's other atoms like oxygen or sulfur or nitrogen, we'll see those. Those are going to be written as letters in this line formula.
Oh, okay. will we know like which other atoms, we'll just do the symbol?
Right.
So, like,
So there's an O for oxygen.
yeah,
And if it was a nitrogen, it would be an N.
oh, okay.
Yeah, because we could make this a little different. And we could make this NH2. And that would be NH2 down there. Yes?
So whenever there's a line extending off that's not labeled, that means that it's a carbon?
At the end, yes. Anytime you have a line that just ends in nothing, the end of it is a carbon with however many hydrogens it needs. So here we've got our skeleton down, but we need to give all these carbons 4 bonds. And so those will be hydrogens all over the place. And there's some really big molecules in chemistry, and writing all the hydrogens gets really tedious. But we use all these different types of structures because they're useful for different reasons. So here's a table showing, I should know how to pronounce this guy's name, but I don't. I'm not going to try it. We usually just call this a structural formula, or the expanded structural formula, where we show everything. This is the condensed formula. So we've got carbon with 3 hydrogens, that's CH3, CH2, CH3. The bond line, or the line bond formula, or the line angle formula, everybody has their own name, is just going to look like this. The end of this line is a carbon, and the end of that line, and the end of this one. So there's 3 carbons, and all of the hydrogens are just assumed. Here we've got one that's got some bromines in it. So in this condensed formula, they popped this bromine up. It could also be shown in line. It's just kind of a matter of personal preference. This could be CH3CHBr, CH2CH2Br. There's a carbon, and whatever is immediately after the carbon, before the next carbon, is attached to the first carbon. Here's the carbon, and here's what's with it, and then that one is explicitly shown. Here's the carbon, those 2 hydrogens are on that carbon. Here's the carbon, H2Br, all 3 of those atoms are bonded to this carbon. It just takes a little getting used to, a little bit of looking at. And if you can look at the X's and O's that football coaches use to write out plays, you can figure this out. That was for the guys in the class. What do girls look at? Well, like instructions for doing crafts, like knitting or something. You've got all these funny symbols. And if you can learn how to interpret those into what you're supposed to do with the yarn, you can learn how to do this. I don't know, how do cheerleaders diagram their choreography? I wasn't a cheerleader. Anyway, analogy gone bad. It works for the guys. My kids play football. Let's look at the next one. So this one's more complicated. Here we have carbon with a double bond to the oxygen, and so that's shown in here. And here we have a double bond between 2 carbons, so that's going to be shown as a double line in the formula. So CH3, let's do, so this is the CH3, and then we've got the CO, and then we've got CH and CH2. So we're just kind of doing a shorthand. We're condensing the formula. For the line angle, here we've got 1, 2, 3, 4 carbons. Those are our 4 carbons that are in this line here in a chain. The second carbon has a double bond to an oxygen, and there's a double bond between the last 2 carbons, so that's shown as a double line. In this one, we've got a triple bond. So this carbon has a hydrogen on it. Now, sometimes at the end, they'll put the H before the C. But you could do it the other way. It would be okay. I wish, they could just do it the same all the time, but they don't. So either of these is acceptable. This triple bond has to be between carbons. Hydrogen can't form a triple bond with anything. Here we have the triple bond. Now this is a little different because we have this triple bond and the single bond, and they're in the same line. There's no angle. What is the angle around this carbon? What is the geometry around that carbon? How many groups are there? There's 2. It's a linear, and so usually in the line angle drawing, we will draw it linear because that's actually the shape of it. The double and the single bonds are always going to have angles like that. Any questions? Isomerism. Let's see, that's another topic.